And let me just recall the statement. So we said if x is, well, let me label it KV3. If x is smooth projective, with SNC divisor delta, and with the coefficients AI strictly less than 1, greater than or equal to 0, and L is a line bundle or a Cartier divisor, such that L is equivalent to M plus delta, where M is a big enough Q divisor. So in particular, these AI are rational numbers. Then the cohomology of OX, KX plus L is 0 for I greater than 0, or the Serre-Dual statement that HI x OX minus L is 0 for I less than the dimension. I want to rephrase KV3 just in a way that often comes up in the proofs that we're going to do of the cont theorem and the contraction theorem and stuff. So, and let me just call this KV3 prime. Because it's really the same thing, just slightly rephrased. Let X be a smooth projective variety. And let's say that delta is some Q divisor of the form sum of di di, but now I'm not assuming anything about where the coefficients di live. I'm just assuming that it's a Q divisor. So they don't have to be between 0 and 1. And let's say we have some other divisor d, which is of the form L plus delta, where L is Cartier. Yeah. And so we have this d of the form L plus delta, where L is Cartier, and assume furthermore that d is big enough. And finally that if we take the part of delta with coefficients, if we take the part of delta whose coefficients are not integers, so another way to write that is that if you round up delta and then subtract delta, then we want this to be simple normal crossings. Or maybe I should say more precisely, the support is simple normal crossings. Then hi of x with coefficients in kx plus the roundup of d is 0. Okay, and this really is just a rephrasing because we take basically we look at delta prime is this roundup of delta minus delta itself, which has this SNC support, and then the roundup of D is the same as D plus delta prime, where D is big enough. And of course, the round down of delta prime is 0 because, well, we're rounding up and then subtracting. So we get something that's strictly smaller than 1 for all the coefficients of delta prime. So then this is really just like applying KV3 to the pair x delta prime and the divisor D. Or I guess L is D plus delta prime because M, the big enough divisor, is D. But anyway, this version just comes up in a few places where it's easier to just manipulate with these roundups and round downs than it is to actually write everything out in terms of different boundaries. Any questions? Okay. So using KV3, then we get a generalized version of Grauert-Riemann-Schneider vanishing, or at least generalized from the version that came up in the proof. So let me write that out as a corollary. And it's certainly not the most general version. But which I'll usually just abbreviate as GR vanishing. So let's say F from Y to X is a morphism between projective varieties. And I think I want to assume birational here, though there's you can slightly generalize to assume that it's generically finite. And let's suppose that Y is smooth. And actually, let's equip Y with a divisor. So let's suppose that we have a divisor delta, so that Y comma delta is S and C. So Y is smooth and delta is S and C. And with this KLT condition that the round down of delta is 0 and delta is effective. So equivalently, the coefficients are between 0 and 1, strictly between. Let's say L is a Cartier divisor with the usual assumption, well, with one difference. So let's say that L is equivalent to M plus delta, where we're only going to assume that M is Neff. Then we have vanishing of push forwards. So I'll say A Neff Q divisor. Then RIF lower star OX KX plus L. Sorry, KY. I'm on Y right now. KY plus L is 0 for I greater than 0. Okay, so maybe the key thing here is that we have this slightly weaker assumption that M is just Nef. But on the other hand, we have to assume that Y is smooth. Later in the class, we'll prove Kawamata-Viehweg vanishing for KLT pairs, and that'll give us a version of this that looks very similar, but where M needs to be big and Nef, but Y doesn't have to be smooth, basically. So the trade-off here is if you allow Y to be smooth, then you can weaken the conditions on M. Okay, and the proof is using the same lemma that we proved last time that relates the vanishing of these push forwards to the global vanishing of cohomology on Y after pulling, like when you tensor with the pullback of an ample. So let's say we fix H ample on X. Then our lemma told us that Ri F lower star Y Ky plus L is 0 if and only if Hi on Y of whatever our bundle is, tensor the pullback of RH is 0 for all R very large, or for all H ample enough. But now we just look at this pullback. So we have KY, well, let me just look at the L piece. So we have that L plus F upper star RH. We can write this as M plus F upper star RH plus delta, because L is equivalent to M plus delta. And so since M is Nef, then M plus the pullback of an ample is also Nef. So this is Nef. But it's also big because F is birational and H is big. So you still have dimensions worth of growth rate for your space of sections because you're pulling back this ample by a birational map. And in fact, this is why you could really generalize this to make F generically finite, because the same will be true when you pull back by a generically finite map. But for us, we just care about birational. So here, this is big in F, and then delta satisfies our assumptions. So then this is 0. From the third version of Kawamata-Viehweg vanishing. And so then by that lemma, the push forwards are 0. Okay. And I should remark maybe the classical version of Grot-Riemann-Schneider vanishing, which follows from this more general version, so often applied to say that the push forwards of the canonical sheaf are 0. Because so that's one of the advantages of only needing to assume that M is Nef, that we can take in particular M to be the 0 divisor. And then when M is a 0 divisor, and when delta is a 0 divisor, and then Y is just some smooth variety, and we have a proper birational map, then we actually get that the higher direct images of omega are 0, which is what came up in a special case in the proof earlier. So that's often how you see Grout-Riemenschneider come up in literature, is that it says that when you have a birational map from a smooth variety, then the push forwards of omega, the higher push forwards of omega are 0. So I should say that in this proposition, because of this, the way that we proved it, we had to assume that x and y are actually projective. Because note, it really comes up in this lemma, because in this lemma, we're relating this higher push forward being 0, which is some local question, to this global cohomology where we really need projectivity to talk about vanishing of this global cohomology. But the conclusion of the actual corollary of the actual Grout-Riemenschneider vanishing is a local question on X. So you really want it for any projective morphism, not just for a morphism between projective varieties. And so I'll just say remark. So you can extend this and the relative KV vanishing that we'll prove in a little bit, where it follows the same structure. To the case where the morphism is projective, but the varieties themselves might not be projective, by taking a projective compactification. And just carefully, so compactifying, resolving, and carefully keeping track of what's happening at the boundary. But the point is, you should believe that it shouldn't change anything, because in the end, the vanishing we get is really a local statement. So as long as you can pick some compactification and then resolve so that the boundary is nice, and keep track of all your divisors, so that you get this, so that this global argument applies to prove vanishing for this higher push forwards, then the higher push forwards will vanish on your original morphism as well, because this is a local claim. Okay. Any questions about that? Okay, so now we're finally ready to prove the KLT version of Kawamata-Viehweg vanishing. So I guess just continuing the proof, but maybe I should restate it from last time. So this is what I called KV4. Let x comma delta be a projective KLT pair. Where well, I guess I should be a little more formal. Let L be a Cartier divisor. Actually, here we're going to prove it for the Cartier case, but we can weaken it a bit. Such that L is equivalent to M plus delta, with M a big enough Q Cartier Q divisor. I should point out here, when I say that we can actually weaken it a bit to only assume that L is Q Cartier, we still want L to be an integral divisor. Otherwise, you have to clear denominators. So we're going to prove it when L is an integral Cartier divisor, but really it also holds if L is an integral but Q Cartier divisor, as opposed to this M, which is a Q Cartier divisor, which also can have Q rational coefficients. Anyway, okay, so L is equivalent to M plus delta, where M is big enough, and sorry, that's it. Just where M is big enough. Then HI x OX of KX plus L equals 0 for I greater than 0. Okay, so this is the version that we'll actually use over and over again because we'll be working with KLT pairs. Okay, proof. And of course, the point was that we needed, not only did we need to prove the smooth case first to take a resolution, but also, and we already saw this in the proof to go from like the ample version of Kawamata-Viehweg, where you have ample plus boundary, to the big enough version. We needed to resolve there, even though X was assumed to be smooth, and so we needed this like Graubart-Riemann-Schneider vanishing in the argument. And so the same idea is here. We needed to first prove this generalized Graubart-Riemann-Schneider vanishing, so that we can understand how to reduce this vanishing to a resolution. So we need to understand the push forwards. But it's essentially the same argument at that point. So pick a log resolution. And let's write our usual formula. So ky plus the strict transform of delta is equal to the pullback of kx plus delta plus our discrepancies. And now, because we want to prove something about this L, which is not just delta, but it's this M plus delta, let's just add M everywhere. So here we have plus F upper star M, and here we also have plus F upper star M. And now by our KLT condition, what do we know? We know that these AIs are strictly bigger than -1. That was our KLT condition. So let me call this whole divisor, let me just denote it EY. So now we want to kind of finagle this around. So let's round up this EY, because like we want to push forward and get something about vanishing downstairs. So we need to rearrange things so that the push forward of whatever's on our right-hand side is the divisor that we started with, is kx plus delta plus m. So we really want this piece to be effective. We don't want it to just be exceptional with coefficients greater than -1. So to do that, we're just going to replace it with the roundup EY on this side. And so to make the equality still true, we have to add something to the other side, and we have to add this thing that I'll call CY, which is just whatever you get when you add the terms you need to this EY to round everything up. So CY is some expression of the form sum of CI EI. And now the key point is that because of this KLT condition, when we round up, all the coefficients of the roundup are now greater than or equal to 0. So the roundup is effective. So that's where the KLT condition comes up. On the other hand, because we're rounding up, then these CIs, the things we have to add on the other side to make the equality true, are all strictly smaller than 1. Because that's just always true when you're rounding up. And so now we get KY plus F lower star inverse delta plus CY plus F upper star M is equivalent to F upper star KX plus delta plus F upper star M plus this roundup, which is effective and exceptional. And on the other hand, this CY is effective normal crossings because we took a log resolution, and with the round down being 0. Okay, and now we're just going to push forward and apply our Grauert, Riemann, Schneider vanishing. So note that note that f upper star m is big in F because it's the pullback by rational morphism of something big in F. And then let's just define delta y to be the strict transform of delta plus the cy. And now y comma delta y is an SNC pair with delta y effective and KLT, so and the round down being 0. So now on delta on y comma delta y with the big and F line bundle f upper star m, we can apply our Kawamata-Viehweg vanishing. So we get that hi on y that this is 0 by kv3. But now if we use our equality of divisors up here, right, I guess I wrote equalities, but I should have written Q linear equivalence. This is the same as the cohomology of the pullback of OX of KX plus delta plus M plus this effective exceptional piece. So tensor, or just twisted by the roundup of EY. Okay, and of course this is for I bigger than 0. Okay, but now we want to push forward and relate this to the cohomology of the thing we care about downstairs. So so now the key point is that f lower star of f upper star ox, sorry, oy, no, ox of kx plus delta plus m twisted by this roundup. This is the same as just the push forward of the pullback of ox kx plus delta plus m by the same argument as in the proof that the push forward, that when you have canonical singularities, the push forward of omega y is omega x. So in that argument, what we really said was that whenever you're twisting by effective exceptional divisors for a birational map, then when you push forward, they don't contribute any sections. And so the same thing holds true here because this roundup is effective and exceptional. So this push forward is the same as the push forward of the untwisted sheaf. And I should add an errata there that I made a mistake that somebody pointed out on Discord. So if you haven't seen that, you should read the Discord conversation. But the argument still goes through. It's just that you really need to induct on dimensions and show that the push forward, so show that like not just O of effective exceptionals don't have sections, but O of effective exceptionals twisted by any degree 0 line bundle, or by any NEF line, numerically 0 line bundle don't have sections. Essentially any divisor that's supported on exceptionals and that is strictly negative, that satisfies the negativity lemma, can't have sections. Anyway, okay, by same argument as in the equivalent characterization of canonical singularities. On the other hand, this is OX by normality because the push forward of O is O. Because the map's birational, and so we get that. Okay, now we need, so we get that the push forward of the thing here that vanishes. So we have the cohomology of this F upper star, whatever twisted by this exceptional stuff vanishes. And now we know that when we push that forward, we get the thing that we want to vanish. And now we need to apply the Leray spectral sequence and apply our Grauer-Riemann-Schneider vanishing. So now by GR vanishing, the push forwards, the higher push forwards of I'll write it as OY of F upper star KX plus delta plus M plus this roundup, which is the same as the push forward of this guy is 0 because Y is smooth and this satisfies the conditions on Grauer-Riemann-Schneider vanishing. So delta Y is normal crossings, effective, the coefficient's less than 1, F upper star M is Nef. So this whole thing is 0. And so by Leray spectral sequence, we get that the cohomology downstairs is the same as the cohomology upstairs. Is 0. Okay, so that gives us Kawamata-Viehweg vanishing in the KLT case. Any questions? Okay, and now this next corollary, I won't write down the proof. It's exactly the same thing that we did here. Basically, every time we have a vanishing theorem, we can then apply this argument to get a vanishing theorem for push forwards by perturbing by some ample. So we'll do that now with our stronger KV4, our Kawamata-Viehweg for KLT pairs. So we'll get relative Kawamata-Viehweg vanishing. So let's say that F, and I'll start using this notation that comes up a lot. Let's say that F from X comma delta to Z is a projective or a morphism of projective varieties with X comma delta KLT. And let's assume that delta is effective. So again, the coefficients are between 0 and 1. Then if L is a Q-Cartier divisor, again, integral divisor, Q-Cartier integral divisor, with L equivalent to M plus delta, where now we're in the relative case, so we don't need to assume that M is F big and F nef. Sorry, we don't need to assume that M is big and F. We only need to assume that it's F big and F nef relative to this F. So where M is F big and F nef. So if you remember, F big means the restriction to the generic fiber is big, and F nef means the intersection with all curves that are in the fibers of F are greater than or equal to 0. Then the higher push forwards of Kx plus L are 0. Okay, so again, this looks very similar to relative Grauert-Riemann-Schneider. So the difference is here, X can be singular because it can be KLT. But M needs to be big NF, not just nef, but it only needs to be big NF relative to F. It doesn't have to be globally big NF. And the other one, Y had to be smooth. M just needed to be nef, but it really needed to be globally nef, not just nef, not just relatively nef. And Y needed to be smooth. Okay. And the proof of this is exactly the same exact argument. We'll just apply KV4 with that lemma. So I'll leave that as an exercise. And really, this in the end, this is the kind of the most general statement that you need to remember because it recovers the other Kawamata-Viehweg statements. So the next thing I want to discuss is the failure of Kawamata-Viehweg vanishing when you have log canonical pairs. So, or equivalently, when you allow the coefficients to be 1. So really, we saw in the proof, the coefficients being strictly less than 1 came up because we needed to use these cyclic covers to absorb the cohomology of L into the cohomology of just the M piece to kind of get rid of this delta. And for those cyclic covers to work, we really needed the coefficients of delta to be strictly less than 1 because in the cyclic covers, you saw all the twists from like 0 to M minus 1, where M was the denominator. But you can still wonder to what extent is it true when you do have some coefficients 1. So let's just do an example to show that in general it will fail. But this example, I think, illustrates kind of why it fails. So I'll write it as the failure of KV vanishing when the round down is not 0. So where you have some components of coefficient 1. So it's just our usual example of some cone. Those are really the easiest examples to get your hands on. This time, let this be the cone over an elliptic curve. And then we're going to take its resolution. Here is an elliptic curve in P2. So a smooth cubic curve in P2. Take its resolution. This is the total space of O of 1. And now on this, we have our exceptional divisor, which is the elliptic curve itself. And we're going to actually add another divisor, which downstairs is a line through the cone point, and upstairs becomes just a fiber direction of this total space. And so now, using the fact that E is a degree 3 curve, we know that, what did I use for my notation? Let's actually, just to make things a little simpler, let's take this orange divisor to be 3 lines, because then that's a generic hyperplane section of the cone. So the orange divisor is a hyperplane H of the cone inside of P3, inside of where it's naturally embedded. And then when we go upstairs, it becomes three lines, three fibers on this bundle, and then plus some multiple of E. So let's let M be the pullback of H. So this is big enough because it's the pullback of an ample. And now we're going to let L be M plus E. So our boundary delta is just E with coefficient 1, and our pair is this total space X with this E. And so this is a simple normal crossings pair. In fact, it's just a smooth variety with a smooth divisor, but the coefficient is 1, so this is a log canonical SNC pair. In fact, it's a little better. It's DLT. But okay, so that's our divisor. Now the claim is that the cohomology of this L does not vanish, even though it's of the form big NF plus boundary. So to see that, we're just going to write down the sequence for twisting by E. So now M, if we don't add this E, then M itself is big enough. And so if we apply Kawamata-Viehweg vanishing to just M, where the boundary is empty, so the boundary is 0, then H1 of OX of M actually does vanish. So we apply our Long's X sequence, we get this is 0. And in fact, H2 is also 0. And so H1 of L is the same as H1 on the elliptic curve of L restricted to E. But now L restricted to E is the pullback of H plus E restricted to E. The pullback of H restricts to E is just 0 because it's the exceptional curve. And E restricted to E, well, this was a degree 3 embedding. E squared is minus 3. Or another way to say it is that E restricted to E, this normal bundle, is O of minus 3 times hyperplane. Sorry, I'll just write it as is degree minus 3. Okay, so then that has cohomology because it's a degree minus 3 line bundle on an elliptic curve. Okay, so what's really going on here? The issue is that this L, when we restrict it to E, it's still equal to M restricted to E plus E restricted to E. But the issue is this M doesn't have enough sections on E. This M is just trivial on E. In particular, it's not big on E, and so there's no reason for this H1 to vanish on our curve, and that implies that this H1 can't vanish upstairs either. So the issue is that M fails to be big on the non-KLT centers. Because in this case, for this log canonical SNC pair, it's everything's smooth, so the only non-KLT center is just the divisor with coefficient 1. And because we assumed it's log canonical, I'll probably usually refer to this as log canonical centers, but those only make sense when the pair is actually log canonical. But then this tells you what to do. You just add that as an assumption, and then you get a log canonical version of Kawamata-Viehweg vanishing. So I'll write it this way. There's many more generalizations of this, but I'm just going to write one simple statement because we're not going to use it later, at least for a while. So we won't need the much more subtle but more complicated versions. So let's say that F from x comma delta to z is a projective morphism with x smooth and delta SNC boundary. And so recall, whenever I say boundary, I mean the coefficients are between 0 and 1 as well. So delta is in particular effective. And let L be equivalent to M plus delta, where L is Cartier, and 1, the usual assumption that M is F nef and F big. And 2, this extra assumption that M restricted to each component of the non-KLT locus is big. Or really is F big. We just need to assume that it's big relative to this map down to Z. Then we get Kawamata-Viehweg vanishing. Okay, and the proof is to induct and essentially use the exact same sequence that we used to produce this counterexample, and just see that under these assumptions that can't happen anymore. So first we'll induct on dimension because that sequence involves restricting to something on lower dimensional. So if the dimension is 1, then the theorem's true. This is actually slightly more subtle than it seems, I guess, because you really have two cases in dimension 1. X is either P1, in which case Kx is -2, but we're assuming that this L is of the form big NF plus effective. So M has to be at least O of 1, or sorry, L has to be at least O of 1. And so Kx plus L is at least O minus 1. And so in dimension 1, it really reduces the fact that O minus 1 also has vanishing cohomology on P1. And then, of course, if X is higher genus, then the canonical is already effective. So Kx plus L just has degree strictly positive. So it's ample. So I guess now that I think about it, there's still something to prove there, because you can have ample divisors that are not that don't have cohomology vanishing. Oh right, then sorry, then we just use serduality because it's this adjoint bundle. It's not just any bundle whose degree is positive, it's actually of the form kx plus L, where L is positive, and so then you use Serre duality. Okay, right. So that's why the theorem is true for curves. So suppose that n is greater than 1. And now we also are going to induct on the non-KLT centers that we need to care about, basically. So those are exactly like what came up here. Here, the thing that gave us trouble was the components of the divisor with coefficient 1. So we'll just induct on those. So let's look at the round down of delta, write it as the sum from r equals 1, or I equals 1 to r of di. So here everything's an integral divisor. These are the components of coefficient 1, and now we will induct on r as well. So if r equals 0, then that's the same as saying that the round down is 0, and so we get usual kV vanishing in the S and C case. So I guess this was kV3. So suppose r is bigger than 0, then pick one of these divisors in your round down, say d1. And now we're just going to look at the same sequence where we twist by this d. So we have 0 to OX of KX plus L minus D1 goes to OX KX plus L, goes to the restriction OD1 KX plus L restricted to D1. It's our usual twisting sequence. Now, this KX plus L restricted to D1, I can manipulate that a little bit. So I can write this as KX plus D1 plus L minus D1 restricted to D1. And now by adjunction, this is K D1 plus L minus D1. So restricted to D1. So that's where our induction is by dimension is really happening, because now we are looking at a sheaf or a divisor of the form canonical plus boundary on a lower dimensional thing. And of course, so D1 is smooth, and L minus D1 is the sum of the other divisors in delta. And when we restrict those to D1 by the S and C assumption, those will also be S and C. So this whole thing is an S and C divisor, and D1 is smooth by our assumptions. And so now, by induction on dimension, we get that Ri F lower star OD1 K D1 plus L minus D1 restricted to D1 is 0. So note here, I'm using the assumption that M, yeah, I guess I should have written this out too. So L minus D1 restricted to D1 is equal to M restricted to D1 plus, the sum of AI DI from I equals 2 to R restricted to D1. Or maybe not R, because R was our index just for coefficient 1. So let's call it S. So this is where our assumption that this is still big comes in. So this is F big plus F nef by assumption. Okay, so that lets us apply our induction to D1, so we get this vanishing of R1 F lower star, and now we have to deal with this other case, but here we have one less divisor. So now here we use the induction on R. So Kx, or let me just write L minus D1 is M plus something with one less divisor, and so Ri f lower star Ox kx plus L minus d1 equals 0 by induction on R. Okay, and so then the thing in the middle by the long exact sequence also vanishes. Okay, so all these are for I greater than 0. Okay, so that gives us one version of Kawamata-Viehweg vanishing in the log canonical case. If we're at least in the smooth SNC case, then we have to assume that essentially that M restricted to each of our divisors with coefficient 1, but really to our log canonical centers is still big. And then there are more general versions where same idea, you have to assume that M restricted to any of your log canonical centers is big, but now you have to worry about that resolution, because when you take a resolution, you have this log canonical center where your divisor is big, but then you're blowing it up. So when you blow it up, maybe it had higher codimension, and now it becomes a divisor when you resolve. So now big means something else, because now the dimension is different. So you have to kind of reducing the general log canonical case to this one is a little tricky, because when you blow up, you're changing the dimensions of your log canonical centers. So you need to somehow carefully modify your delta and your M to get an appropriate theorem in the general log canonical case. But we won't need that in this class, so we're not going to do it. Any questions? Okay, so in the last 15 minutes, we can finally state the full form of the fundamental theorems that we talked about at the beginning of the class in the form that will actually prove them, which is for KLT pairs. So Kolar-Mori calls them all the cone theorems, because they're the theorems that you need to prove the cone theorem, including the cone theorem itself. So let's do that. And they don't have names attached to them, so let me just write down the various names of people who originally proved these theorems in these forms in the 80s. So Mori, Kawamata, Reed, Shokurov, and Kolar. But in various combinations and for various pieces of the arguments and for various levels of generality. So this is all done in maybe 80s, early 90s. Okay, so first one is the base point free theorem. Now we can really state it. So in the full generality, we already used this theorem in the case of surfaces to show that minimal surfaces of general type satisfy the abundance theorem. And there I just kind of brushed it under the rug that we need the KLT version, even there. Even there where the surface is smooth, we still need the KLT version, because we needed to add some kind of epsilon times some divisor and know that that pair was KLT. So we have this base point free theorem. So now we can really state it. Let x comma delta. And I should make one more comment. I'm going to state all these theorems in the projective case. Some of them have weakenings to the proper case. Basically, whenever the theorem only requires this kind of relative vanishing, which holds for these type of statements do hold more generally with some work and understanding birational maps and compactifying, like taking projective compactifications of things. But we're just going to work in the projective case for simplicity. So let x comma delta be a projective, and also some of the theorems just don't work in the like the cone theorem. You have to assume projective because even the cone of curves being well behaved and Kleiman's criteria and all these things require projective. But some of these vanishing theorems hold slightly more generally. And maybe another comment is that basically from now on, anytime I write delta, it'll be effective. For these theorems, I'll write it down as part of the hypothesis. But yeah, basically delta is always effective, even though we defined KLT and log canonical, all these other notions for divisors that are possibly not effective. Whenever we see delta, it'll be assumed effective, though we will see in one of the theorems where allowing the KLT pair to have non-effective divisor does come up. Okay, so let delta be effective, and let's say D is a Neff Cartier divisor. Such that the combination AD minus KX plus delta is big enough for large A. So for some large A. Then D is semi-ample. I.e. BD is base point free for B large enough. And I should really write the name. This is the base point free theorem. Okay, and another way to think of this, a lot of these theorems are sometimes phrased, including the Kawamata-Viehweg vanishing. We didn't phrase it this way, but oftentimes they're phrased in this form of AD minus log canonical divisor satisfying some property. But the way you can think of this is just that call this M, and then this theorem becomes if kx plus delta plus m is Neff, and m is big enough, then kx plus delta plus m is semi-ample. So this is reminiscent maybe of the abundance conjecture, but in this log setting, but with the difference being that here, to get semi-ampleness, we needed to add this big and Neff divisor. Okay, so that's the base point free theorem. Then we have the non-vanishing theorem. And we proved some kind of non-vanishing theorem in the case of surfaces. So let's say X is projective, and D is Neff. And G is just some Q divisor. Satisfying the following properties. One, again, this kind of difference property, but this time there's a minus G. So let's say we have AD minus KX minus G is a big NF Q Cartier divisor. For some A. And two, let's assume that the pair X comma minus G is KLT. So this is one place where we're talking about KLT pairs where the divisor is not necessarily effective. It can be effective, doesn't have to be. So because we didn't make any assumptions on G here other than that it's a Q divisor. Then we have the following non-vanishing or existence of sections for the divisor MD plus the roundup of G for all large enough M. So let's give us a condition on some divisor having sections. So next we have the rationality theorem. So X delta is projective KLT. Delta is effective. And fix some integer M greater than 0 such that M times KX plus delta is Cartier. And if you want, fix the smallest such M. And now suppose that KX plus delta is not an F. Then we can do this thing that we did in the case of surfaces where there we didn't have a delta, we just had KX, but we said suppose KX is not an F, then take some ample divisor and approach the cone by writing ample plus R times KX. So do that same type of thing. Fix H, but now we actually don't need H to be ample, we can just let H be big and F. So fix H, A big plus F. So we have some extra flexibility. Q Cartier divisor. Again, this could be a Q divisor. And let's define this Neff threshold, just like before, but now with a boundary there. As the supremum over all T and R, such that H plus T KX plus delta is Neff. Then the theorem is that this R is rational, but actually not just rational, but we have some bounds on its denominator. So R is a rational number in Q, where we can write it as U over V, such that this V is bounded by M times dim X plus 1. So that's where this M comes in, this Cartier index of KX plus delta. Okay, so that's the rationality theorem. And then finally, we have the cone and contraction theorem. So I'll end today by writing down the cone and contraction theorem, and then we'll start next class outlining how these theorems are proved. And I mean, really, they build off each other, so what the logical relations are, and then actually starting the proof. So let me write down the cone and contraction theorem. Just because it's a lot longer, I'm going to spin the screen so that we can fit it all. So let X comma delta be projective KLT pair. Again, with delta effective. Then we have the following 4 parts. There exist rational curves, countably many. Such that we have a bound on their degree with respect to KX plus delta. And that bound is 2 times the dimension. So in particular, they're KX plus delta negative curves. And a decomposition of the effective cone into the piece where kx plus delta is non-negative, plus this countable sum of rays corresponding to the numerical classes of these CIs. So basically the kx plus delta negative part of the cone is rational polyhedral locally, well, right now, rational polyhedral spanned by countably many classes of rational curves. And then 2, it's locally finite in the following sense that for any ample divisor H, then we can perturb by epsilon H a little bit. Then we get that any of x is any x where kx plus delta plus epsilon H is non-negative, plus a finite sum of these rays spanned by the CI. Oh no. And then 3, we have contractions. So if f in any of x is an extremal face, which is kx plus delta negative, so it's spanned by some finite collection of these countable rational curves CI, then there exists a unique morphism, phi f, or also called contraction of f, from x to z, such that phi f lower star of ox equals oz, and phi f of a curve is a point if and only if the class of the curve is in our face. And then finally, for any line bundle or Cartier divisor L, such that L dot C is 0 for all curves contracted by our extremal contraction. So we're still in the setting as in 3. There exists a line bundle or Cartier divisor downstairs such that the pullback of this LZ is our L. So basically, for these extremal contractions, any line bundle that looks like it descends actually does descend.